Hello everyone, welcome to this lecture on the Lorentz transformations. This lecture is a part of module 6 of your course on electrodynamics, which basically deals with relativistic electrodynamics. So essentially the idea here is to integrate the electromagnetic theory with the relativistic concepts. So this lesson will be more or less like a recap, mainly a recap of your concepts from special theory of relativity that you would have probably gone through in your undergraduate courses. So first we'll be just looking at the postulates of relativity and the mechanics of relativity, followed by the familiar Lorentz transformation. Then I will introduce to you what is known as a Minkowski SpaceTime, which I'm not sure if you would have already done in your undergraduate course. Mostly no. So I'll be introducing to you the idea of Minkowski SpaceTime, which enables us to write down the Lorentz transformation in a much more succinct form. And then I'll introduce to you the idea of the space-time and the structure of the space-time. Then we will build upon the concept of what is known as the four vectors, because this is a concept that we actually require if we want to build our relativistic electromagnetic theory. So the ultimate idea is to be able to describe all our the equations that we had derived in our electromagnetic theory in terms of very simple elegant equations, and these equations involve what are known as four vectors. And finally we will end with a qualitative discussion on how relativity is actually a bridge between electric and magnetic fields. So our starting point here would be the principle of relativity. So we all are familiar with principle of relativity because this is one of the first things that we learn in school in your physics. So this is a very old concept which was already known to us since a long time. In fact, it was known to us since Galileo's time. So the principle of relativity it basically says that the laws of physics will remain the same and will remain invariant in all inertial reference frames. Now what is an inertial reference frame? An inertial reference frame is any frame in which Newton's first law is valid. That is, an object at rest or an object at uniform motion will continue to be in that state until and unless an external agency acts on it. Of course, Galileo was not aware of Newton's laws, so he did not call it as inertial reference frames, but he just said that when you change your point of view, okay, you go from one point of view to another point of view, the laws of physics they will remain the same. So as a result of this, as a consequence of this principle of relativity, it was able to account for the fact that flow of time seems to be constant across all inertial reference frames. And of course now we know that it is not true. The flow of time is also relative, which is actually given to us by Einstein's special theory of relativity. Now let's explore this a little bit further, because is the principle of relativity, is it applicable in electrodynamics? At first glance, the answer seems to be no, right? Because as per the principle of relativity, a frame could be at rest or it could be in uniform motion. The laws of physics should remain the same. So if I take a charge to be a frame, the charge could be at rest or it could be in moving with a uniform velocity. The physics should remain the same, but we know that is not true, because a charged particle which is at rest, it gives rise to only an electric field, but a charged particle, when it moves with a uniform velocity, we call it as a current, and that gives us a magnetic field. So the physics did change compared to when the charge is at rest and when the charge is moving. So at first glance, it seems that the principle of relativity, it is not valid when you talk about electrodynamics. But let us now have a look at a certain coincidence which actually baffled physicists initially. The scenario is basically this. I have a pair of magnets, okay, north and south pole facing each other, and these two magnets, they are stationary, and then I have a conducting loop, and this conducting loop is moving with a velocity v. There is no battery which is attached to this conducting loop. So now if I make this conducting loop move through these two magnets, then we will find that there is a current is going to be set up in this loop. So where does this current arise from? this current arises from what is called as a motional EMF. Okay, motional EMF, if you remember from your undergraduate course, it is basically due to the magnetic force on charges inside a conductor. So as this conducting loop, as it moves through, then the charges, they experience a magnetic field, and then they start moving in this loop, and this gives us a electric current passing through this. So I mean, this was of course the foundation of the Faraday's law. So you can actually work out the directions of the current that is going to be set up. So once it will be set up in one particular direction, and as it moves out, the current will be set up in the other direction. So because current, when they move, when there's a flow of current through a conductor, there must be some EMF. So we can actually find out the EMF in this loop, and this EMF turns out to be equal to minus d phi v by dt. This can be easily shown using the concept of motional EMF. I'm sure you would have probably done this in your undergraduate course. But here the observer is stationary standing with the two magnets. The observer is stationary. Now let us consider another observer who is moving along with this loop. So that observer who is moving along with this loop, for him the loop is stationary and the two magnets, they are moving. So this is how it will look like for a person who is moving along with the loop. Okay, so we'll have the two magnets coming in, and then the same observation will be seen in both the cases. Obviously the observation has to be the same because it's the same physical reality. So as the magnets move in, he finds that this moving observer finds that first the current flows in one direction, and then again the current flows in the other direction. Now if you want to explain this, then we can use the concept of induced EMF, right? Induced EMF. And induced EMF, in this basically it says that a changing magnetic field produces a changing electric field, and that changing electric field will cause the charges in this conducting loop to move. So that means the source of the EMF will be the induced, this will be basically the electric force on the charges, and we can find out the EMF, and in this case also the EMF will be the same. So now think about it. In both the cases, okay, we have changed our reference frame. So this is also an inertial reference frame, okay, because we are stationary here, we are stationary along with the magnet, and this is also an inertial reference frame. You are moving with the loop at a constant velocity. Both of them are inertial reference frames. In both the cases, we have found that the EMF in the loop is the same, but the way we have calculated the EMF is not the same. In the first case, in this case, we have calculated the EMF by considering the magnetic force which is acting on the charges. Okay, so the force acting on the charges will be due to the magnetic field. But in this case, the force acting on the charges will be due to electric field, because of course your magnetic field is changing, but that changing magnetic field induces a changing electric field here. So it's an electric field and this electric field is going to cause the charges to move, and we get an EMF. So the physics seems to be different in these two cases, because that's what was actually expected. People thought initially that the principle of relativity is not applicable in case of electrodynamics. So because these are two different reference frames, the physics should be different, and of course that's what it turns out. Here the physics is that the charges move due to magnetic force, and here the physics is that the charges move due to electric force. So the physics is different, but the result is the same in both the cases. We get the same result. So this was something which actually people at that time, they thought that maybe it's just a coincidence. At that time means in the late 19th and early 20th century, people thought that it is just a coincidence that the EMF turns out to be the same in both the cases. But Albert Einstein he refused to believe that this is just a coincidence. In fact, he believed that the fact that the EMF in the loop is the same in both the cases, even though the physics is different, that is an indication that the principle of relativity is also applicable on the electromagnetic theory. In fact, he had mentioned this in this was the starting point of his 1905 paper on special relativity. I mean, no doubt, I need not stress how important this paper is, which in terms of radically changing our view of the world. So this is basically this is the first page of that paper. I have provided the link to this paper and in my references. So basically that's what he's talking about. This same example, the same example that we have seen here, he's basically referring to these examples, and it says Examples of a similar kind and the failure of attempts to detect the motion of the earth relative to the light medium lead to the conjecture that not only in mechanics but in electrodynamics as well, the phenomena do not have any properties corresponding to the concept of absolute rest. The other example that he said was the failure of attempts to detect the motion of earth relative to the light medium. Any basic, if you would have undergone a basic course in modern physics, or maybe in an introduction to this relativity, so over there you would have probably heard about the Michelson-Morley experiment and their attempts to find to detect the presence of the light medium, or which was referred to as the ether, and it failed actually. So Einstein is basically talking about this. He's talking about this previous experiment that we had discussed, and the failure of this experiment, such as Michelson-Morley experiment, to find the motion of the earth related to the light medium. Basically, the attempt was made by this experiment to find out the state of absolute rest, and this led Einstein to conjecture that the phenomena do not have any properties corresponding to the concept of absolute rest. There is nothing called as absolute rest, but that in all coordinate systems in which the mechanical equations are valid, and also the same electrodynamic and optical laws are valid, as has already been shown for the quantities of the first order. So he's basically starting with his paper with the conjecture that the principle of relativity is applicable on electrodynamics just the same as it is applicable on mechanics. And he further says that we shall raise this conjecture to the status of a postulate. Okay, so this conjecture, which is basically a principle of relativity, he says that we shall raise it to the status of a postulate. Okay, so that's and shall introduce, in addition to the postulate, that in empty space light is always propagated with a definite velocity v, which is independent of the state of motion of the emitting body. So this what I have highlighted here in green is basically the second postulate. So this is basically the first postulate and this is the second postulate. So these two were raised by Einstein. So the principle of relativity, he called it as the first postulate of relativity, and he introduced the second postulate, which of course he mentions in his paper, that in empty space light is always propagated with a definite velocity v, which is independent of the state of motion of the emitting body. So we can say the second postulate is that light moves with a maximal invariant speed, which is independent of the inertial reference frame which is chosen. So this of course was inspired by the failure of the Michelson-Morley experiment, as was mentioned in Einstein's paper. And it shows this second postulate, it demonstrates that the flow of time is relative. The principle of relativity says that the flow of time is constant across all inertial reference frames, but the second postulate, it actually tells that the flow of time is relative. How time flows, it changes from inertial reference frame to inertial reference frame. So now I'll just have a quick recap of the relativistic mechanics that we have already studied in your undergraduate courses, just to refresh, just to jog our memory. So we have this velocity addition. The velocity addition equation, it changes. Suppose I'm having three different bodies, 1, 2 and 3. 1 and 3 are moving and 2 is stationary. Okay, so 1 is moving, 3 is moving and 2 is stationary. Then we can find out the velocity of 1 with respect to 3, the velocity of one moving body with respect to the other moving body, using this equation. So v13, velocity of first moving body with the other third moving body, is equal to velocity of the first moving body with respect to the ground plus the velocity of the ground with respect to the third moving body, divided by 1 plus same product of these two velocities divided by c square. So this is your velocity addition equation. In our ordinary case, this quantity will become almost zero. So as a result, it will give us that familiar equation in that we have learned in our high school, that is v13 is equal to v12 plus v23. Next we have what is known as the relativity of simultaneity. That is, two events which are simultaneous in one inertial reference frame are not in general simultaneous in another. So an example of that was that familiar Gedanken experiment that Einstein had performed, where there is a train, and inside the train at the center, right in the middle, there is a source of light which emits light, and there are two detectors at the two ends. Okay, so a person who is moving with that train will see that, these suppose you have the light which is emitted, you will find that the light hits the two ends of the train at the same time. So that means these two are simultaneous. But somebody who is standing on the ground will find that these two, they do not hit at the same time. Another version of this experiment is you have a railway station. I think that was the one which was actually narrated by Einstein. You have a railway platform, you're standing right at the center of the railway platform, then lightning bolts strike simultaneously the two ends of the platform. You will find that the two bolts, they are simultaneous, they have hit both the ends of the platform simultaneously, but a person who is traveling on the train will find the lightning bolt closer to him has hit first, and the lightning bolt which is farther away, it has hit later on. So it means in one frame, for you it was simultaneous, but for the person who is moving on the train, the two events, they were not simultaneous. So that is basically the relativity of simultaneity. Then we have the familiar time dilation. Basically it says that moving clocks, they run slower. So let's say I'm having one event, okay, a set of let's say two events which are separated by a certain time interval. Okay, a person who's stationary is observing this, and a person who is moving is also observing this. So these two people will observe differently. The person who is stationary will observe a certain time. The person who is observing, who is the moving observer, will observe that the time has actually increased. Okay, so this is basically your time dilation. The faster you move, the slower your clock is going to run. And finally we have the Lorentz contraction or the length contraction. So if I am a stationary observer and I am watching something which is moving very fast, then I'll find that the length along the direction of travel, the length is going to decrease. That's your Lorentz contraction or the length contraction. So this is basically like your relativistic mechanics is all about all these. Then before we go to Lorentz transformation, I'll just define this idea or the notion of event, because I've used this word event some time back. So I'll just this is a good place where I will to actually explain what an event is. So event is basically the instantaneous physical situation or occurrence associated with a point in space-time. So an event is basically, you could think of an event just like you have in space, in three-dimensional space, every point will have 3 coordinates. An event will be it exists in space and time, and which we call it as space-time. So an event is basically just like your point, which has got 3 coordinates, but in addition to the 3 space coordinates, it will also have 1 time coordinate. So total it will have 4 coordinates. So that's basically an event. So event is you could think of a coordinate system, a 4-dimensional coordinate system. Three of these coordinates are the space coordinates, and 1 coordinate is the time coordinate. So any point in this will be basically an event. So you could have an event which two different events. The time should be different. So you could have, it's possible that 2 different events are taking place at the same position, but they could be taking place at 2 different times, so they will be 2 different events. So it could be like maybe your birthday, you celebrate your birthday at your home every year. So 2019 you had celebrated your birthday at your home, 2020 also you celebrated your birthday at your home. These 2 are 2 different events because the position may be same. You have celebrated your birthdays, both these birthdays at your home, but the time is different. They are apart from each other by 1 year. So that's why they are 2 different distinct events. Then we talk about the moment we talk about events, then we also talk about what is known as a space-time interval. So space-time interval is basically the separation of 2 events in 4-dimensional space. What is the separation between one event and another event? That is known as a space-time interval. So this is analogous to distance or displacement in 3 dimensions. Okay, so I have one point, another point, the displacement between them. So the space-time interval is analogous to that. So suppose I am having 2 events which have a spatial separation of delta d. Okay, so one event and another event, they are separated by a distance delta d, by a displacement delta d. So delta d is equal to the displacement along the x plus displacement along y, displacement along the z. Of course I'm writing it in a much more haphazard manner over here. It's not like this. This will be delta d is actually equal to under root delta x square plus delta y square plus delta z square. So here I have written this just to stress upon that this delta d is basically a combination of all of this. Okay, and they have a temporal separation of delta t, that is one takes place at one time, the other takes place after a time interval of delta t. Then the space-time interval between these two events will be delta S square. Okay, we always take a square here, is equal to delta D square minus C delta T square. So this will be equal, delta D square is equal to delta X square plus delta Y square plus delta Z square minus C delta T square. So we can actually distinguish between space-time intervals depending on whether the space-time interval delta S square, whether is it positive or negative, because it can be, because it's a difference, right? So here we have delta D square and here we have minus C delta T square. So this quantity can be positive, negative, or it can be 0. So if this quantity is negative, okay, if this quantity is negative, that is delta S square less than 0, then we say that this space-time interval, we call it as time-like. If it is equal to 0, that is this quantity is equal to this quantity, then we call it as a light-like space-time interval. And if it is positive, that is if delta D square is greater than C delta T square, then we call it as a space-like. The idea behind this terminology is, so we consider an event which takes place at the same position but at different times. Okay, so it is at one point, and after some time, it remains at the same position, and after some time something happens. That's another event. So an example could be, let's say you have taken an apple and you have put it on a table, okay, and you leave it for 5 days. So that apple is going to go bad, it's going to rot, right? So so you come back, and when it rots, you again pick it up. So the instant of time when you placed it on the table and the instant of time when you lifted it from the table, these are two different events, right? They both take place at the same position. So in that case, delta D will be 0. If delta D is 0, then delta S square will be minus C delta T square. It will be negative. That means it depends only on the change on time. So that's why it's called as time-like. In a similar way, the other way around, we call it as a space-like. And why is it called light-like? Because if delta S square, if it is equal to 0, okay, delta S square, if it is equal to 0, this quantity, entire quantity, if it is equal to 0, this means C delta T square is equal to delta D square. You could remove the square here, so it will give us C delta T is equal to delta D, which gives C is equal to delta D by delta T. Delta D by delta T, D is displacement, delta T is the time interval. So displacement by time, this will give us velocity, which is equal to C, and C is nothing but the speed of light. So that's why it's called as a light-like space-time interval. Okay, so Lorentz transformation, what are they? Is basically a set of equations that transform a set of coordinates from one inertial reference frame to another. So let's say I'm having one frame, the stationary frame S, and I have a moving frame S tilde, which is moving with a velocity v with respect to the stationary frame. And this point P, it's not a point, it's actually an event. Okay, it's this point P is basically an event because it takes place at a certain position and at some time t. Now this point P, which is observed by the stationary observer, it will have the coordinates x, y, z and t. And this moving reference frame also observe the same event, and it will find that its coordinates are x tilde, y tilde, z tilde and t tilde. Okay, so the Lorentz transformation, it gives us a way to convert from one inertial frame to another inertial frame. That is, if you know x, y, z and t, okay, if you know x, y, z and t, you can find out x tilde, y tilde, z tilde and t tilde. So that is your Lorentz transformation. You could also have a inverse transformation. That is, if you know the coordinates in the moving frame, you can find out what will be the coordinates in the stationary frame. In that case, you just have to replace v with minus v, so you'll get a plus sign here and you'll get another plus sign. So this is basically your Lorentz transformation. Essentially, there is no difference between these two. Okay, it's just a matter of putting the sign of this v. So that's basically the Lorentz transformation. So before we proceed further, let's have a look at what is known as I'll introduce to you the notion of the space-time diagram. Okay, so now let's see what happens here. Here the red frame, okay, the red frame, we are going to consider only a two-dimensional frame because I'm going to add a time axis also. So let's say I'm having a two-dimensional frame. Okay, so the red color frame is the stationary frame and the blue colored frame is the moving frame. Okay, so let us say I have a blue colored frame which is moving at a velocity with respect to the red color frame. So this is how it is going to move. It is going to move from left to right. Okay, so let me just pause this here and take you step by step. Okay, initially both of these frames, they are coinciding. Then next instant of time this moves forward, next instant of time it moves forward, another instant of time it moves forward, and it moves forward, and so on. So it keeps on moving, so at different instants of time. So initially it's here, and at different instants of time it moves forward. So if I put a time axis over here, if I put a time axis along the vertical, then this can be represented in terms of what is known as a space-time diagram. So this is what will happen. So initially both of them, they coincide. Just go back. Initially they are coinciding. This is the initial instant of time. Next instant, okay, this frame, it has moved. It is not going up, okay, because you see up, it's only the time axis. It is moving forward in time, so it has gone towards this side, and in time it has moved forward, then it moves some more forward in time, like this, and so on. So this is basically a representation of what's happening here. So what's happening is moving forward. I just added a time axis here, and I'm representing the same thing what is happening in this case, in this diagram. So this basically is how a space-time diagram, this is how it works. Okay, so space and time, they are separately, they are not invariant. Okay, so space, if you change from one frame to another frame, the coordinates is going to change. So the distance between 2 points will obviously change. Okay, so space is not invariant. Similarly, the time interval between two events also will not remain the same when you go from one frame to another frame. So it means different observers, they will disagree. So I'm having two different observers in two different frames. Both of them, they will disagree on how much time has passed between two events. Why will they disagree on the interval of time? It's because of time dilation. Okay, they will also disagree on the distance between two events. Why will they disagree between the distance? Because of length contraction. Okay, so because of time dilation and because of length contraction, two observers will disagree on space and time separately. So we say that space and time separately, they are not invariant. That means they do not remain the same across inertial frames. But special relativity, it shows that it is the space-time interval between the two events which is always invariant. Okay, so individually space and individually time may not be invariant, but the combination of space and time, and we call it as a space-time interval, which I had explained some time back, that combination will always be invariant. Okay, so an example of this is, let us say I have a LED light, a multicolor LED light, which can change its color. So initially it is emitting a pulse, a yellow color pulse. After some time it is emitting a green color pulse. Okay, so it is lying on the table. Okay, so this LED is lying on the table. Initially it emits a yellow pulse. Okay, it switches on, it releases a yellow pulse. After some time it releases a green pulse. Okay, so this is basically what is happening. So this is the first event and this is the second event. Okay, so we want to find out what is the space-time interval between these two events. Now we want to find out the space-time interval between these two events using the two different frames. One frame is a stationary frame and the other frame is a moving frame. Okay, so we will try to find out what happens in this case using these two different frames. So the stationary frame, what it says is, because the LED is stationary, you will find that okay, initially it is yellow. After some amount of time, as it is seen on the y-axis, okay, previous slide I had already shown you, this is how a space-time diagram works. After some interval of time it becomes green. So in this case delta x will be 0. So the space-time interval that will be calculated will be c delta t whole square. Of course there is a minus sign here, which of course I have removed it because I just multiplied the whole equation by a minus. Okay, so that's why. So there is going to be actually a minus, think of it as minus. So the space-time interval that will be calculated will be delta x whole square minus c delta t whole square. So delta x is 0, so it will be minus c delta t whole square. So that's the space-time interval that will be measured by the stationary observer. Now I have an observer who is moving from left to right. Okay, so we have this blue one. This is the observer who is moving from left to right. So how will this observer observe these two events? Okay, so the observer is moving from left to right. So initially it is on left and it is moving towards the right. So initially it is far away. The LED is far away from the observer. So when the LED was yellow, it was far away, and when the LED is green, it is closer to the moving observer. So initially it is far away, and finally when it is the second event takes place, it is closer to the observer. Next, again, what about the time interval? Will the time interval be same? It will not be same. Because of time dilation, the moving observer will find that compared to the stationary observer, the time taken between these two events will be more. Okay, so delta t tilde will be larger, and delta x tilde will be also non-zero. So the space-time interval that the moving observer will observe will be c delta t whole square minus delta x square. So over here, c delta t tilde square, it has increased, but at the same time there is a delta x tilde whole square also which is there. So the combination of these two will turn out to be equal to the space-time interval here. So space-time interval measured by the stationary observer will be the same as the space-time interval measured by the moving observer. You can actually work this out over here. You can just substitute this delta t and delta x, okay, using the Lorentz transformation, and you can actually show that this is indeed the case. Okay, so now you can see when I write it as a full equation, you can see why I did not put the minus here, because there was a minus here and there was a minus here and this was plus. I just multiplied the whole thing with a minus sign, so that's why we had a plus sign here. So the fact remains is what we should be taking back from here is using special relativity, we can show that the space-time interval between two events is always invariant. So using the Lorentz contraction, and using the concept of time dilation, we can show that these two space-time intervals will be just the same. So this is basically the fundamental reason why we want to merge space and time into space-time. So that will give us an invariant quantity, which is the space-time interval. So next we'll go to what is known as a Minkowski space-time. So what is Minkowski space-time? It is basically a combination of three-dimensional Euclidean space and time into a four-dimensional manifold. Okay, manifold, I'll not go much into the details, it's a separate topic by itself. So locally it will be Euclidean. Okay. So where the space-time intervals between any two events is independent of the inertial frame of reference in which they are recorded. So this is basically a Minkowski space-time. So it's a combination of three-dimensional Euclidean space and time into a four-dimensional space, such that the space-time interval between any two events is independent of the inertial frame of reference in which they are recorded. Okay, so this Minkowski space-time was developed by a German mathematician known as Hermann Minkowski. He had basically developed this in order to write down the Maxwell's electromagnetic theory in a much more concise form. Later on, it was shown by Einstein that the Minkowski space-time is a natural consequence of special theory of relativity. So Minkowski space-time is not the same as a Euclidean, four-dimensional Euclidean space. In mathematics, we talk about it in general n-dimensional Euclidean space. But Minkowski space-time is not the same as a four-dimensional Euclidean space. That's why we call it as a 3D Euclidean space and time into a four-dimensional. We call it as a manifold. The reason is one of these coordinates, which is a time coordinate, it is one of the dimensions, which is a time dimension. It is treated in a different way compared to the other space dimensions. The space dimensions, they are equivalent, but the time dimension is not equivalent to the other three space dimensions. So that's why it's not a four-dimensional Euclidean space. So the x, y, z coordinates and t coordinates, they are redefined in this way. So the x coordinate, okay, ordinary x coordinate, we write it as x1. Ordinary y coordinate, we write it as x superscript 2. And ordinary z coordinate, we write it as x superscript 3. Okay, so you have to read it as x1, x2 and x3. Do not think that this is x to the power 1, x to the power 2, x to the power 3. It's not that. Okay, it is just we are putting our identifiers of the coordinates as the superscript. Okay, and of course there is a last coordinate which is related to a time coordinate, that is x4. x4 is simply I into speed of light into the t. Okay, so this is how you redefine the coordinates. Okay, now why do we use the superscript? Because over here it's not going to make much of a difference. You can use subscripts also, but when you go forward from special theory of relativity, when you go forward to general theory of relativity, and over there we have to bring in curved space. We need to bring in the curvature of the space. So there we need to distinguish between two types of vectors, two types of tensors. One is known as a covariant, another one is known as a contravariant. So there we distinguish between them using superscripts and subscripts. In one case it's a superscript, in the other case it's a subscript. So, but nevertheless, it's a good idea to get used to this practice of writing the coordinates as this indices as superscripts instead of subscripts. So this is how you redefine. This is the Minkowski spacetime. Okay? These are the 4 dimensions. Okay, the first 3 are the space dimensions, and the last one is the basically the time dimension. So x1 is x, x2 is y, and x3 is z, and x4 is simply ICT. Or you could just turn them around. Okay, that is, if you know x, y, z, t, you can find out. If you know x, y, z, and t, you can find out what is x1, y, x2, x3, and x4. Conversely, if you know x1, x2, x3, x4, you can find out what is x, y, z, and t. So x is nothing but x1, y is nothing but x2, and x is not, sorry, this is z. Please read this as z. Z is nothing but x3, and what is t? T is nothing but x4 divided by IC. So the 4th Minkowski spacetime coordinate you have to divide by IC. That will give us time. So we'll just call this as equation number 1. And if you recall the Lorentz transformation equations, so these are the Lorentz transformation equations. So now we will use equation number 1 first in equation number 2. Okay, so we'll use equation number 1 in equation number 2. All you have to do is basically wherever we have this x, y, z, and t, you replace them with x1, x2, x3, and x4. That's what we will do. And of course we will introduce this beta. Beta is nothing but v by c, the relative velocity of the part of the flame with respect to the speed of light. So beta is equal to v by c. So using equation 1 in equation 2 and introducing this beta, so this is what we will get. So we have not done anything extraordinary. What we have done is this x, okay, this is the x coordinate. This x coordinate I write it as x1. Of course there is a tilde here, so I have to put the tilde also. Then there is a gamma here. Then we have another x coordinate here. This x coordinate I'll write it as x1. Then there is a v here, velocity v. I'll write it as beta into c, because v is equal to beta into c. And then there is a t here. T, like we saw, t is equal to x4 by ic. So I'll replace t with x4 by ic. And this we can write it as, okay, there is a gamma here, gamma times x1, gamma times x1. And there is a I in the denominator. So the moment I take this I into the numerator, so there will be an additional, we'll have to include another minus sign. That minus and minus will give us a plus. So this I goes into the numerator and we'll get a plus here. Then there's a gamma already here, and there's a beta here, and this c will cancel out with this, and as a result what will be left behind is I gamma beta into I gamma beta x4. So gamma x1 plus I gamma beta x4. So we'll write this in a more formal way. So we say that x1 tilde is equal to gamma times x1 plus I gamma beta times x4. And just for the sake of completion, I am also including the other 2 coordinates, that is x2 and x3. And because this x2 and x3 they don't appear here, I'll just multiply them with 0. So 0x2 plus 0x3. This is called as equation number 5. We'll do the same thing with equation number 4 now. Okay, with equation number 4, just using equation 1 in equation number 4, and also again introducing beta here. So equation number 4, so we have a tilde t here, t tilde. T is nothing but x4 by ic. So it will be, because it's t tilde, it will be x tilde 4 by ic, which is equal to, there's a gamma here, then this t will become x4 by ic minus v is equal to beta c by c square, and this x is nothing but x1. So this will give us gamma x4 by ic minus gamma beta by c x1. This is what we have. Now multiply this throughout by ic, and when I multiply this throughout by ic, we will get x4 equal to, we will get a, here this x1, multiply this by ic, c will get cancelled, there is a I which will come here, and there is already a minus sign here, so we will get a minus I gamma beta x1, and this ic will get cancelled here when you multiply throughout. Then we'll be left with gamma x4, and again for the sake of completion, x2 and x3 will just include them with 0 coefficients. So we'll call this as equation number 6. Now do the same thing for the equation number 3, which is going to be really straightforward. Equation number 3, what it says is y tilde is equal to y. So what is y tilde? What is y? Y is nothing but x2. So y tilde is nothing but x tilde 2. Okay, x2 tilde, and which is equal to x1 will be 0.
Okay, y tilde is equal to y, which is equal to x2 tilde is equal to x2, so there will be a 1 here, rest everything will be 0. Similarly for x3, okay, there will be a 1, the coefficient 1 for x3, rest everything will be 0. So these are your equations 6 and 7. So this is what we have. Now the moment you look at it, immediately one thing that strikes you out is, okay, so we have a vector here, okay, and we can combine this vector with another vector, that is this vector x1, x2, x3 and x4. Okay, so this is the vector x1 tilde, x2 tilde, x3 tilde, x4 tilde. This is one vector, and we have another vector x1, x2, x3 and x4, another vector here. And whatever all these coefficients that we have, we can take these coefficients together and replace it with a single matrix. So this 4 equations can be combined into a single matrix equation like this. Okay, and we could also write it more simply as vector x tilde is equal to L into vector x. So call this equation number 9. So we have equation number 9 is basically the matrix representation of Lorentz transformation. But actually this is not surprising. We should be able to express it as a matrix equation, because it's, after all, it's just it's a transformation, right, from one set of vectors to another vector. And if you recall your course on vector spaces, okay, that we did in the previous semester. So if you recall that I'm having one vector space, another vector space, and we are having a transformation from one set of vectors to another set of vectors. So there should be a transformation matrix. Okay, so that transformation matrix is the Lorentz transformation matrix, which is given in this way. And in terms of elements, we could also write it as xi tilde is equal to Lij xj. Okay, so of course ij, okay, so I is the row index and j is the column index. We don't write them as L subscript ij. I take this as I as the superscript and j as the subscript. Okay, why the reason why we behind this terminology will become much clearer when you undergo your course on general relativity. So let me stop right here for this part of this lecture. So in the next part we will continue, we'll discuss some of the structure that is there in space-time, and then I'll introduce to you the idea of 4 vectors. Okay, so we will stop here. See you in the next part.